and I'll do the screen share with 5.4. Okay. And I'll move this thing out of the way. And I'll move Jordan out of the way. He's in the way here. Okay, I'll scoot you over to the right. Okay, so let's start the slideshow. We don't need to start it from current slide because we are on example 2. And why this isn't popping up now, I think. There was example 1, and we wanted one slide before that. Okay, so let's now go from current slide. All right, we've already done example 1. Now that we are recording, do you have any questions, issues, concerns, especially concerning calculus? Okay, so these will be recorded, or anything else? Nothing? All right. Okay, well then let's pick up where we left off last time. Hold on just a moment. It's getting a little stuffy this morning. It was cool enough in here. Let me turn on my ceiling fan to make it a little more comfortable in here. And since example 2 is not on the slide set, we'll go to the whiteboard and do that. Now here again we have to do some adjusting. I want to move this taskbar as far out of the way as possible, and then move the whiteboard as far in the other way, so I get maximum white space. I don't think you can see anything but white space, but I have a limited amount of white space here. All right, let's go with example 2. Now, okay, now here's what we're asked to evaluate. The integral from 0 to 2 of the absolute value of 2x minus 1 dx. Boy, they jump right in with this one, don't they? Now, what we have to do here is identify that function inside, because it is a continuous function, so we can integrate it, but it's not a smooth function. So this is not going to be something particularly easy to do. What we do here is rewrite what's in here as a piecewise defined function. That's 2x minus 1, the absolute value of 2x minus 1. Its definition is two x minus 1 anytime 2x minus 1, this is a stupid way to write it, but is greater than 0, right? Greater than or equal to 0. And it's the opposite of that. So I'm going to rewrite this as 1 minus 2x anytime 2x minus 1 is less than 0. Do you agree with that? It's the value of it anytime that thing is greater than 0, but it's the opposite of that anytime it's less than 0, right? That's what absolute value means. Now, what makes more sense is to solve these inequalities here. So let's add 1 to both sides, and you get 2x is greater than or equal to 1. So that means x is greater than or equal to 1/2. And this one does the same way. It would be x is less than 1/2. So this is these are our new parameters here. So let me write this. Here's what it is. It's 2x minus 1 anytime x is greater than or equal to 1/2, and it's 1 minus 2x anytime x is less than 1/2. Does that make sense to you? Absolute value is the value of it anytime the thing that's in there is positive. Okay, so that's what I wrote up here. That's why I wrote it that way. And it's the opposite of that anytime what's in there is negative. Well, we solved these things here to give us actual x values. Now we see this is a two-part integral. The first part is the integral from 0 to 1/2. That's this point, and that will be this value here, 1 minus 2x dx, plus the integral from 1/2 to 2 of the second part, and that would be 2x minus 1 dx. And you might want to put those in parentheses. I don't know. If you like parentheses, do them. It might make it easier to see and understand. All right. Now, that was the hard part of the problem. The easy part, let me just make sure everything's doing right. Yeah. The easy part is doing the antiderivatives. What's the antiderivative of 1? Oh, x, perfect. Minus, and what's the antiderivative of 2x? X squared. We'll evaluate that from 0 to 1/2. Plus, and these same antiderivatives, x squared, I'm going to put this in parentheses here, and perhaps I should this one too, okay, minus x this time, and this will be evaluated from 1/2 to 2. All right, let's do the work here. This will be a 1/2 minus 1/2 squared is 1/4. And I like the zeros because I can do those. That's nothing. Okay? Plus 2 squared is 4 minus 2. That's when you plug 2 in here. Minus 1/4. And then you got a minus, watch those, which is plus 1/2. All right, that's what you got. Notice you got 2 minus 1/4. That adds to minus 1/2, so that wipes out the plus 1/2. 4 minus 2 is 2, plus 1/2 is 2.5, or 5/2. Okay, let's see. Oh, that's what the book got too. Now, I know I did that fairly quickly. Did y'all have any questions on it? Were there any steps in the process there that I went too fast and lost you? Anybody? Excuse me. Sorry. Choking on something. Grabbed a few almonds on my way up, and I guess one of those pieces went down the wrong way. Sorry. Any questions on this? Does this make sense? Our first integral as a piecewise continuous interval has to be continuous, but it doesn't have to be smooth. If it's not smooth, break it at that point where it's not. You know, the absolute value function always graphs something like this. Okay, so this is not smooth down here. So we did it, the area here and then the area here. That basically is what we were doing. I didn't draw the coordinates in there, but that's what it is. You'll see it in your book. If you look in your book, you see that. Well, in case some of you don't have books, let me ask this. Do all of you have books? Yay or nay? No. Okay, well, let me show you what that looks like then. This is the absolute value. No, it isn't. Where is it? There it is. There's the function we're just dealing with. Notice the v goes up more sharply because it's 2x minus 1. It's also offset by 1/2, and that's because when you write that in the form of x minus something, it's x minus 1/2. So it's offset to the right 1/2, goes up sharply, and that's the area that you're trying to do. The first integral was from 0 to 1/2, the second integral from 1/2 to 2. Add those together and you got the areas. That's hard to hold. Okay. Any questions on that? All right. Neither do they have number 3 on the PowerPoint. So is it all right to clear the screen? Okay. Now, I'm trying to think. Yeah, we had Screencast-O-Matic on Monday, but again, I want to ask you, remind me at the end of the class when we are leaving, turn off Screencast-O-Matic. I didn't do that last Thursday and piled one class on top, not on top of the other, but in the same recording. So this part of the recording was one class, that part was the other class, and I had to explain to both those classes how to navigate that. All right, so here is example 3. Find the area of the region bounded by the graph of y is equal to 1 over x. Okay, the x-axis, rather than writing x-axis, I'm going to put y is equal to 0. That is the x-axis. It's just easier to write than writing the x-axis. The vertical lines, x equal 1 and x equal e. Ooh, interesting. That's an irrational number, e. Okay. Now, just a quick look at this. When x is equal to 1, y is 1. When x is equal to e, e is about 2.7. So let's just round it for 3 for right now. So that will be going to something a little bit greater than 1/3, because you put e in the denominator, and that would be something a little bit greater than 1/3. So it's going from 1 to 1/3. Okay, positive everywhere there. Pretty short thing. So, and you're going from the y-axis. So basically, that is your integral then. The integral from 1 to e of the function 1 over x, maybe you see why they chose e now, times dx. Okay, that's what we're integrating. Now, you see the y is equal to 0 means you're going from the x-axis, so that doesn't really enter the picture here any. That's what your integral is doing. Now, can anyone tell me what the antiderivative of 1 over x is? Please say yes. Okay, now I understand what you're doing. Let's take a look. You're trying to use the product rule, right? So let's rewrite this using the product rule. Using exponents, okay? Which is not a bad thing to do in most circumstances, except this one, okay? Because if you did the power rule here, I say product rule, power rule here, then you would have this, you increase this by 1, that would be x to the 0, and then you divide it by that new exponent, 0. Nope. Okay, you took a derivative of it, kinda. The derivative of x to the minus 1 would have been x to the minus 2. We're not doing derivative, we're doing antiderivative. So this is a no-no. Okay, this is the one and only thing that looks like a power function that you don't use the power function. No, 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 no. All right, any other guesses? boy. No, that you would have to have a 1/2 somewhere in there, and you don't. No, no. That would have been if it had been an x to the minus 1/2. You're absolutely right. This is x to the minus 1. You cannot use the power rule here, so don't even try. Okay? Now, this is sort of a special function. And I would almost hope that the fact that we have an e here might suggest something to you. It shouldn't. They're just trying to make it easier. The antiderivative of 1 over x is, anyone else want to make a guess? Natural log of x. Because the derivative of log x is 1 over x. So the antiderivative of 1 over x is log x. Now most of the time we put that with absolute value bars around it, except your interval here from 1 to e is all positive. So you don't need the absolute value. So we just put the interval here from 1 to e. Okay? Now, fundamental theorem of calculus says we evaluate that how? Log to the e minus log to the log of 1. Anyone know what log e is? Oh, please say yes. Log is the inverse function of the exponential function. Exponential function, inverse function of the log function. So this comes out 1. How about log of 1? Well, please say yes. Log of 1 is 0. So this is simply 1.
How you got 1 for log of e again?
Okay. Because that's what it is. Okay. Okay. Let me make a reference for you. Okay. Because it's hard to do without the actual. Let me see. I think it's going to be easier to go to the table of contents. If you go back to goodness gracious, where is it? I know it's in here. Oh, here we go. 1.6 on page 52. Do you have your book?
I got it on
Ebook?
yes, sir.
Can you pull it up now, or since you're watching this, you can't pull it up?
I'll put it up real quick.
Okay. If you go to page 55, near the bottom of the page, you'll see this statement. I'll write it down for you. The log of e to the x, because this is a natural log. If this is base 10 log, this won't work, but it's a natural log of e to the x is this, okay? It's equal to x. And e to the log x, because they're inverse functions of each other, that's going to be x, okay? Because the log function and the exponential function are inverses of each other. Now in our case, the x is 1 because it's log of e to the first power, right? They just didn't write it down because it's a 1, okay? Well, this would then be log of e to the 1 would then be 1. And also e to yeah, the log of 1 would be, let's see what that comes out to be. Log 1 is 0, like we just saw here, so that'd be e to the 0. What's e to the 0? Anything to the 0 is 1, and sure enough, that's exactly right. So they're inverse functions of each other, which means these two statements here are true, always true. Okay? And just remember, you can't take the log of either a negative number or of 0. But if you remember, e to the x is never negative and never 0. Now it can be awfully close to 0, but it's never 0. And same thing here, you can only take the log of positive numbers, but so x has to be positive in this case, but e to the anything is always positive, so that makes sense too. So this is about the best I can do, is refer you back to what it means to be inverse functions of each other, and this is what it means. Remember back in precalculus algebra when you said f of f inverse, that means f inverse of x is equal to x, and f inverse of f of x is equal to x. That's what it means to be an inverse of each other. These twos are inverses of each other. Log and exponentials are inverse of each other, so therefore when you do the log of the exponential, you get x. When you do the e to the log x, you get x, because of these two principles of inverse functions. Just happened to be, in our case, x was 1. So that gave you 1. It's a long roundabout answer. Did that satisfy you? Yay or nay? Okay, good deal. Thanks. I don't know if the rest of you can see it. You gave me a thumbs up. Okay. All right. That finishes example 3. Now we're ready to go back to the slide set, which I don't know why that popped up, but I must have hit something. Let's go back to the PowerPoints, 5.4, and we'll go back to current slide. Okay, we finished example 1, 2, and 3. These are just continuing 1. We did those last time. Now we go to mean value theorem for integrals. Okay. I think we we had a mean value theorem when we dealt with derivatives. Now we have one for integrals as well. How does this go? You saw that the area under a curve is greater than the area of the inscribed rectangle, but less than the area of the circumscribed rectangle. Okay? The mean value theorem for integrals states that somewhere in between those two areas, the inscribed and the circumscribed rectangles, there is a rectangle whose area is precisely equal to the area of the region under the curve. And here's a curve. It's a fairly symmetric looking curve about that line anyway. We're looking for the area under this curve, which is the pink area that mixes with the blue down here and you can't tell a difference. Okay, that's the area under the curve. Now the inscribed rectangle would be down here somewhere, the circumscribed rectangle would be up here somewhere, and the area under the curve is in between those. Well, there's got to be some rectangle in between the one down here and the one up here where the area is exactly the same. Okay, and that's what we mean here. This area here, they're going to say, and sure enough, it looks like the little light blue area here overshoots this part in here, but the pink area here undershoots the part here. I mean, the part here undershoots that by that much. this one overshoots this by that much. And it sure looks like to me that the area of this and the area of that are just about equal. So this is saying there is some point C in between A and B that if you did f of C here and just did f of C times B minus A, you're going to get exactly that same area. And that's what they said here. F of C is the height of this right here. That's f of C right there, because that's on the curve, okay? Times the length of this, B minus A, that's the length of that rectangle. There's the height of it. This area is the same as the area under the curve, okay? Precisely. The thing is, we don't know the C, okay? It'd be nice if we did, but we don't always know what that C is. But you know there's one out there somewhere. And this is what the mean value for, excuse me, integrals is saying. There is some value in between A and B such that f of C, that same function that's in here, times the B minus A is equal to the area under that integral. All right. Now here's it stated as a theorem. If f is continuous, now f has to be continuous, okay? You can't have any breaks and holes and things like that, and it has to be continuous, okay? On the closed interval from A to B, then there exists a number C somewhere on that closed interval A to B such that the area under the curve, that whole curve f of x, that continuous function f of x, is equal to that f of C times A minus B, the length of that interval, okay? Now, that's all they're doing. They do a little proof here, and you can go through the proof if you like. We are running sort of behind, so let's move on to average value of a function, okay? Now, this plays right off of what we were just talking about. That value, f of C, given by the mean value theorem for integrals, is also called the average value of f on that interval. And that sure was what that one looked like, wasn't it? F was a low value down here, a high value up here. That f of C is somewhere smack in between the two of them, and not exactly halfway, because they may have slightly different areas there, but it's somewhere in there. And that's what we're meaning by average value of a theorem, okay? That's also called that. So here's a definition of the average value of a function on an interval. If f is integrable, got to be integral. Now, before we said continuous, okay, for the mean value theorem, this is a little tighter requirement. F has to be integrable, okay? That means not only is it continuous, it's also smooth, okay? Also smooth, okay? Well, not just that either. There can't be any vertical asymptotes there, okay? So that's sort of another thing too. So it has to be integrable on the closed interval from A to B. Then the average value of f on that interval is this thing, exactly like we said. Remember we said before the f of C times A of B was equal to this. So f of C, which is the average value, divide both sides by 1, B minus A. And that's the average value of the function. So what if this is our function here? This is a wiggly squiggly function here going from A to B. Here this undershoots, the function is below the rectangle. Here function is above the rectangle, below the rectangle, above the rectangle. Not by equal amounts either, okay? So this is saying the average value of that function is that f of C. There is some value C. Now look at this. The C could be that C, it could be this C, or it could be that C. There could be several of those values because all those f of C's have that same value. But there's at least one, okay? This one happens to have 3 of those. The average value is this right here. It doesn't matter what the C is, it's the f of C. That's the average value. And that's it right there, okay? also given right there. Okay, so to see why the average value is defined in that way, if you partition A to B into n subintervals of equal length, delta x equal b minus a over n. Oh no, I thought we were through with these, okay? And if c sub I is any point on that I subinterval, then the arithmetic average, or the mean of the function values at those ci's, is, you have n of those, so your the arithmetic average, I wish they didn't use little a here, because we use little a for the endpoint here, but they're using this for the mean. Okay, I wish they'd have used something else like m or something like that. That would be 1 over n times the sum of all those f of c's. That would be the average value, the arithmetic average of that. Okay, now if you think of that, this is the b minus a could, well, let's watch them do it. By writing the sum using summation notation, then multiplying and dividing by b minus a, you can write the average as this. Here was the average we just said. Pull the 1 over n on the outside because it's the I in here, and this was your f of ci. That's exactly what this was here. Summation of all your f of ci's from I is equal to 1 to n. The 1 over n didn't have an I in it, so you can pull that outside the summation. Okay? Now, what they're saying to do is multiply and divide by b minus a. And you might say, why? Well, here's why. Take the denominator on the outside, because b minus a has nothing to do with the summation at all, but leave this one on the inside and pull back that n, 1 over n. Why they put it out there, I don't know, but they did. Well, now what is this? That's your delta x sub I. Go back a page, there's your delta x sub I, b minus a over n. That's why they brought it in. So this is 1 over b minus a from here times the summation I equal 1 to n of f of c sub I times delta x. You could call it delta x sub I or not, it doesn't matter. That is your delta x right here. Yeah, you probably don't need the I in it. Delta x. That is precisely the limit of that is your integral. By taking the limit as n goes to infinity, produces the average value of that, just like we saw. So in this figure, notice the area of the region under the graph is equal to the area of the rectangle whose height is that average value. It's the f of c we're interested in, not which c we're dealing with, just what f of c is. Okay? How we get it? Do the integral, divide by 1 over b minus a. 1 over b minus a. Divide by b minus a. Okay. So here's example 4. Let's do it. Let's do it to it. Okay. Find the average value of f of x equal 3x squared minus 2x on the intervals 0 to 4. So that average value, and we can call it that if we want to, average value, okay, of f. Okay. Now, I don't know if you like to call it f of c or not. You could do that. That's a lot easier to write. Okay, that would be 1 over b minus a. Here's your a, there's your b, so this would be 4 minus 1 times the integral of your f of x, 3x squared minus 2x, I'll put them in parentheses, dx. That's simply what we said it was. Okay, so this is 1/3 of, oh, I left off my limits, from 1 to 4. Okay, now, what's the antiderivative of 3x squared? They gave you a very easy one, didn't they? Anybody? This x cubed minus x squared. Perfect. Evaluated from 1 to 4. So this will be 1/3. Okay, cube 4. 4 times 4 is 16. 4 times 16 is 64. Minus square 4, and you get 16. Okay, then subtract 1 from it. Subtract when you value 1. So that'd be a -1 because it's a minus the 1 cubed. Then it's minus a minus, which is plus 1 squared, which is 1. Well, that doesn't contribute a thing, does it? Okay, so here we have it is 1/3 of, I believe that's 48, isn't it? I hope it is. And I think 3 goes into 48 16 times, doesn't it? Now I'm doing that off the top of my head, but sure enough, the book did it on their head as well. Okay. Any questions on that? Do you see what we're doing, why we're doing it? So the average value of that is 16. Any questions? Let's see how they did it. Now, unfortunately, I can't erase this. Okay, so I'm going to sort of write over it here. The average value is this definition right here, just like we did. 1 over b minus a times the interval from a to b of f of x dx, where b is 4, a is 1, a is 1, b is 4, f of x is 3x squared minus 2x. So this is 1 over 4 minus 1 times the integral from 1 to 4, 3x squared minus 2x dx. They put parentheses in 2. Now they did calculus. 1 over 3, antiderivative of 3x squared is x cubed, minus 1, antiderivative of x of 2x is x squared, evaluated there, and that would be 1/3 of 64 minus 16. Now they put their 1 minus 1 in parentheses. That kind of does help for making sign mistakes. So watch out for those signs. Whatever it takes for you to eliminate those sign errors, do it. Excuse me. Sorry, my throat is scratchy this morning. Okay. This, of course, becomes 0 just like it did for us, and that would be 48 over 3, which is 16. And there's the graph of it. Now, they only showed the graph from 1 to 4, which is all we're interested in. Okay, that's sort of lucky because it was quite likely this is going to go negative down here. And that doesn't really work too well when you're below the x-axis. So you need to stay above the x-axis. So from 1 to 4, you're always above the x-axis. And there's your function. The area under that curve is the pink and blue together here. And the average value is this right here. What do we say? Well, we said 16, which is here. We didn't figure out what the x was that would give that to you, but who cares? Okay, you could get that if you plug the 16 in here and solve that quadratic. More than likely, you're going to come up with an irrational number, which you can do if you wish. Okay, no problem with doing that. All right, so that's example 4. The question is, are they going to do example 5? No, they're not. Now, maybe we won't do it either, but we'll talk through it. Okay? Now, because this is a tedious problem which takes a lot of time, but it's a pretty interesting problem. Okay? Now, in your book is one of the coolest pictures, and I've seen several of them, but there it is. Does anyone know what that is, what's happening right there? Anybody? Yes, you're absolutely right. And a jet aircraft is exceeding the speed of sound. Now, what in the world is that cloud-looking thing, that conical cloud behind the jet that the jet happens to be coming through? Well, that's little particles of moisture. Now look at the sky behind that is perfectly blue, okay? But see, as the jet is moving ahead at close to the speed of sound, it's pressing, because sound waves are compression waves, it's pressing all of the air, which includes moisture, together ahead of it. And when it does go through that, it's now pressed them all together, and so all the moisture that's in the air, even though it looks like a pretty dry, clear day there, it pressed it all together and made a cloud. And then it came through that as it exceeded the speed of sound. So, neat picture. And underneath the picture, they talk about Charles Yeager, who was the first person to fly at the speed of sound, greater than the speed of sound. That was in 1947, by the way. And it gives a few more details. And this is a FA, they usually don't put a slash between them, FA 18F Super Hornet, and it just is, it's pretty interesting. They talk about how it's using a different fuel. The first U.S. Naval tactical aircraft to exceed Mach 1, the speed of sound. I didn't know all that. Pretty interesting. I was in the Navy, okay, but that may have been after my time. Okay. Here's the deal, the reason they give this. If he had been flying at a lower altitude, he was flying up there at 12.2 kilometers above the surface of the Earth. If he had been flying below 11.275 kilometers above the surface of the Earth, he would not have broken the sound barrier, because the speed of sound in air varies with altitude. Okay? Now they draw this as a sort of a jagged curve. I would think it's going to be a little smoother than this, but they're approximating it with probably things they've gotten from linear regression. Okay, here is look at that piecewise continuous function. Your f of x, I think is what they call it, no, s of x, which is the that's the speed of sound, s of s, at different altitudes. X is your altitude. And look at that. Near the surface, it's minus 4x plus 341. Okay? Then a little bit higher, that's from anywhere from x equal the surface of the Earth up to about 11.5 miles, and that's why they said if he had been flying below 11.5 miles, he wouldn't have broken the speed of sound. He wouldn't have broken the sound barrier. Okay, then it's a constant there from 11, I said miles, kilometers, okay, because these speeds are in meters per second, by the way. And then it's 295, constant from 11.5 to 22 kilometers up. Then it starts varying again. This time it was going down, now it's flat, now it's going up, and it goes up at different rates, and then it comes down again. So rather bizarre curve there, and not really sure why it takes such strange values. But anyway, it does, and that's a piecewise defined function. So what they want you to do, it said, what is the average speed of sound over the interval from 0 to 80 kilometers? So that means you have to do that integral, piecewise integral, over each of those pieces, okay? And then divide that, when you add all those up, divide that by 80, because 80 minus 0. That's what they do down here. They do each one of those integrals, and this is probably a good exercise to do, but it would take most of the rest of the class to do all those. Okay, they're not hard integrals, they're not hard at all, but they're just tedious because of all those weird fractional or decimal forms and stuff, and squaring and cubing and whatever. Okay, so they come up with the average speed of sound over that time is about 24,000, oh, I'm sorry, is about 308 meters per second. Okay, and if you'll notice, most of those are not too far off from that. The constants there at near ground level, it's 341. That next interval is 295, then 278.5. So you see they're all roughly in that ballpark. Some are above, some are below. Is it okay with you to skip example 5? As calculus books love to say, it's the rest is left to the student. Okay, all right, Andy says it's fine to move on. Thank you, Andy. That gave me permission. Okay, let's move on to the second fundamental theorem of calculus. Now, if any of you happen to have other calculus books that you're using, you may see this as written Fundamental Theorem of Calculus Part 2. This book calls it Second Fundamental Theorem of Calculus. A lot of books, most of the books I've taught one from before, call it Fundamental Theorem of Calculus Part 2. Okay? But here's what it is. Earlier you saw the definite integral of f on the interval a to b defined using the constant b as the upper limit of integration and x as the variable of integration. However, a slightly different situation may arise when the variable x is used as the upper limit of integration. Now what that means, you can't have x in the integral then. You have to change your dummy variable. So to avoid the confusion of using x in two different ways, oftentimes they use t or some other variable as the dummy variable inside the integral, the variable of integration. Remember that that definite integral is not a function of that its variable because you integrated it out. Okay? So here's what all that blah 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 was saying. When you have a constants here, integral of f of x dx from a to b, that's what it is. But if you have a definite integral as a function of x, capital F now being the, before we called it the antiderivative, and it sort of looks like that same issue here, but now this is a variable function, not a numeric function. This just gives you a numeric answer. Whatever the antiderivative of this is, evaluate it at b, subtract it at a, you got a number. This is going to be a function of x. So you change your dummy variable, your independent variable in here, to be t, and now this capital F of x is the integral from still some fixed point at the bottom, but now you let the upper point be a variable. And then you integrate that same function, f, little f, doesn't matter what you call that, and do the antiderivative of this and evaluate it first to f of x, which gives you a variable, minus f of a, which is a constant. Okay? So, we're going to do it. All right. So here we're asked to evaluate this function at 5 different values for x. So let's first do the integration. Okay? So, what's the antiderivative of cosine t? Anybody remember? Please say yes.
Is it negative sign? Yeah.
Okay. Positive sine of t. Okay? Because derivative of sine is cosine, the antiderivative of cosine is positive sine. And we're going to evaluate this from 0 to x. Well, that's going to be sine of x, right? You plug the x in here, minus sine of 0. But can anyone tell me what the sine of 0 is? 0. Very good. Okay, so that's what it is. So let's evaluate it at 5 different places. Well, we just answered the first one. Sine of 0 is equal to 0. Okay, sine of, oh, this goes back to good old trig days, doesn't it? pi 6. Anyone remember what that is? One half. Sine of pi fourths. Anyone remember that one? Square root of 2 over 2. Excellent. Sine of pi thirds. Anyone remember that one? Square root of 3 over 2. And the sine of pi halves. Anyone remember? One. I don't know what the little noise was, but it was. Now, these were our favorite functional values assigned between 0 and pi halves, remember? And remember the little trick for them? I don't know if you remember this or not. For 0, it's the square root of 0 over 2. This is the square root of 1 over 2. This is the square root of 2 over 2. This is the square root of 3 over 2. And this is the square root of 4 over 2. Of course, square root of 0 is 0. 0 over 2 is 0. Square root of 1 is 1. So this is 1 half. And then these are exactly the same, looking exactly the same. Of course, the square root of 4 is 2 over 2 is 1. So that's the easy way to remember those are favorite values between 0 and pi halves. 0, pi 6, pi fourths, pi thirds, and pi halves. There's your sign. The cosine goes backwards. It starts at 1 here. If this was cosine here, be 1, square root of 3 over 2, square root of 2 over 2, 1 half, and 0. If you went the same values. Okay. All right. That's how we did it. Any questions before I move it? I'm going to leave it up there, but it'll just be written over. Okay. You could evaluate the 5 different integrals if you wanted to. One for each different upper limit if you wanted to, or just do it once. It's much simpler to fix the x as a constant temporarily to obtain that, which is exactly what we did. The integral from 0, this is exactly what they've written there. Sine t evaluated from 0 to x, and when you plug that in, you get sine x minus sine of 0, which is, of course, sine x, and then plug in the values. And then when you get at 0, you haven't gone anywhere. So the area under there is 0. At pi 6, you've just gone a little ways here. Your area under here is 1 half. When you go out to pi fourths, the area under here is root 2 over 2. When you go to pi thirds over here, you're up to root 3 over 2. And when you get the full lobe, this is the cosine function, remember? That cosine function, and it's not a very pretty cosine function, but it is a cosine function. That area under half of a cosine lobe is 1. Because the area under a full lobe of either sine or cosine is always 2. Surprisingly, it's always 2. Okay. So, any questions on that? And this shows sort of again how you can use integration as being a summation as you're moving down a curve and doing the different areas. That's what the second law, fundamental theorem of calculus, can do for you. Okay. It doesn't have to be something simple like the cosine curve, any curve that you can integrate. So you can think of the function f as, this is what I was saying, accumulating the area of the curve as you move from t equals 0 to t equal x. Okay? For x equals 0, the area was 0 because it was 0 thickness. Okay? At pi halves, it has moved to 1 half. I'm sorry, it moved to 1, and then anything in between was between. That interpretation of an integral as an accumulation function is often used in applications of integration. So they say. I don't ever remember using it that frequently except when they're illustrating this. Now, in example 6, which is the one we did earlier, that we just did, note that the derivative of f of capital F is the original integrand with only variable changed. That is, derivative of f of x, remember that was the sine x, derivative of that is cosine x. Well, that was this. Derivative of an integral gives you what was on the inside. Oh, wait a minute. Isn't that a lot like an inverse? But they're not inverse functions, they're inverse operations of each other. An integral is an operation, a derivative is an operation. That result is generalized in the following theorem, which is called the second fundamental theorem of calculus. And here's what it is. If f is continuous, remember it has to be continuous, on some open interval I, containing some value a, then for every x in that interval, the derivative of the integral of f of t dt, now you're going from a to x, that's going to be exactly f of x. Just plug that in here and you get this. It's taking a derivative undoes an integral, just like taking a square root undoes a square. Adding undoes subtraction. Multiplying undoes division. Division undoes multiplication. Logs undo exponents. Exponents undo logs. This is not a reciprocal inverse function. They're inverse operators of each other. The derivative undoes an integral. Okay? Now, that's basically your second fundamental theorem of calculus. Using the area model for definite integrals, this approximation, f of x times some dx there, is going to be approximately equal to the integral of x from x to x plus delta x of f of t dt. Now, it seems like we've jumped another rabbit, but we really haven't gone that far. That can be viewed as saying that the area of the rectangle of height f of x and width delta x, that's not a dx, a delta x, is approximately equal to the area of the region lying between the graph of f and the x-axis on the interval from x to delta x. So, if this is your curve, always positive here, but mostly continuous, it has to be continuous. It happens that this works when it's positive, okay? Now, here's f of x here, here's f of x plus delta x here, okay? So, this thing here, f of x, is that height here times your delta x. That area under there is approximately equal to the area under the curve from x to x plus delta x. Of course, it undershoots it, in this case, a little bit here, okay? That's why it's approximate. Of course, if you let the delta x keeps getting smaller and smaller and smaller, that gets to be a better approximation, okay? Now, hard to see too much of what that's worth, except it's sort of beginning to feel like the integral analogy to a differential. Okay, so don't know if that made sense. So here we say evaluate d by dx, derivative of the integral from 0 to x of this thing in here. Okay. Now, if you go back a couple of slides here, this one right down here, this was f of t dt, we just put x in there. Okay? So your first guess might be just put x in here. So it looks like, on first glance, this would be the square root of x squared plus 1. And that is indeed, note the f of t is that, continuous on the entire number line, because this is never negative. This is always positive. The square root of a positive number is always positive, so it's continuous and above 0 over here, so it meets all the requirements. So all we do is plug in. Second fundamental theorem of calculus says you can just rewrite this as that, which is exactly what we did. Derivative of an integral is whatever the inside is. Okay. That was pretty easy, wasn't it? Now, that was example 7. They skip example 8. Shame, shame. Because example 8 changed something ever so slightly, but enough to make a big difference. So let's go to our whiteboard and let's us do example 8. Can I erase this old one? Okay, I heard no objection, so I'm going to erase it. All right, find the derivative of f of x. Okay, here's your capital F of x. And this f of x is the integral from pi halves to x squared of cosine t dt. Now, that almost looks like its second fundamental theorem of calculus, but not quite. Because, okay, the a can be pi halves, no problem with that at all. But this in the fundamental theorem of calculus should have been an x, not an x squared. Okay, so we have an issue here. Now, if we change this to the integral from pi halves, I hate to even put that here, but I will, to u cosine of t dt, that would be a different story if u was equal to pi halves. So let's make that assumption. Let u, I'm sorry, not pi halves, u equal x squared. Okay, well, if we do that, u du would have to be 2x dx, right? In other words, du dx is equal to 2x. That's probably the better way to phrase it in this case. Okay, now let's think what this is. This would kind of look like it would be that. All right, now the problem said find the derivative. What we're looking for is f prime. We're looking for f prime when f is that. Well, what is f prime? F prime, written in Leibniz notation, is df dx. But if we change that around, that would also be df of u du times, well, let's just leave this off in du, that's supposed to be a u, dx. Okay, now here is where the this comes from. So this is what we're looking for, this, and that is, and this I think would be by this definition here, f of u. My internet connection is unstable, so I'm going to stop until it stabilizes. Okay, did I break up something in there? Anybody? A little bit, okay. That's why I quit doing what I was doing until that sign went away. So if this is what we're looking for, if I can get my pen to come back, where in the world is it? There it is. This thing is that thing, okay? This thing is this. So df du, we know what that is. That is cosine u, because that is the fundamental theorem of calculus part 2. Doesn't matter what this is, that just has to be a constant, okay? But then this is times du dx, but we also know what that is. Well, u is x squared, so this is cosine of x squared times 2x. So that's what the df dx is. Oh my, I missed it. No. Well, I would have gotten it right if I had read properly. The problem was not x squared, it was x cubed. Sorry about that. It's very small print and I'm in the shadow down here. So then everything changes here. This is x cubed. This is 3x squared. This is 3x squared. This is 3x squared, and this is x cubed. Okay, that's the answer. Sorry about that. Cosine x cubed times 3x squared. I wrote it the other way. Okay. Now, that's one way to do this problem. Now, they said because that integral here was so easy to integrate to begin with, you could have just done it brute force and figured out what f of x was. That would be antiderivative of cosine t is sine t. Evaluate that from pi halves. Now this time we are using this, if I can get it to right, to x cubed. This time we'll write it right. So this will be sine of x cubed minus the sine of pi halves. So sine of pi halves is 1. Okay? Then that's your f of x. Now take a derivative of that. Derivative of this would be cosine x cubed, chain rule, times 3x squared, and derivative of minus 1 is 0. So that gives us the same answer as we got there when I used the right problem. Sorry about misreading it. So I think it's actually easier in that case to actually do the integral as it is and then take the derivative of the answer. But it just seems like second fundamental theorem of calculus should make it easier, and it was not bad. All right. Now that was example 8. Now we're ready, excuse me, for, I'm going to have something else to drink. It's a lot hotter up here today than it has been. I don't know why. Maybe it's hot outside too. My throat's drying out like crazy.
Yeah, it's hot outside.
Is it? Okay. Let's go back to the slideshow from the current slide. And now we move page 326 to the net change theorem. Now, not talking about how much silver you carry around in your pocket. That's not what it means. Here's what it means. The fundamental theorem of calculus states that if f is continuous on the closed interval a to b, and capital F is the antiderivative of little f on a to b. Now this is the first fundamental theorem of calculus, the one we did first. Then the integral from a to b of little f of x is just then the antiderivative of little f is capital F first evaluated at b minus a. Okay. Now, because capital F prime is equal to little f, it's the if capital F is the antiderivative of little f, that means the derivative of capital F is little f. Okay, anti, but they're going backwards. That statement can be written this way, that the antiderivative of the derivative of a function is actually the difference in those between the limits. Now this looks pretty familiar, I hope, because what we just did with the second fundamental theorem of calculus, let's go back a slide or two. It says if you take the derivative of an integral, you just get what's inside. Now this is saying if you take the integral of a derivative, you get what's inside, the capital F, what you started with, but you have to evaluate it at two different things. Well, of course you do. When you're dealing with integration, you always are off, could be off by a constant. So that quantity there, f of b minus f of a, represents the net change in f over that interval. Wow. Net change in f over that interval. Okay? Interval could have been doing all sorts of wiggly stuff, but if they happen to be fairly close at the end, didn't have a whole lot of change there. Okay, so here's the net change theorem. If f prime of f is the rate of change of a quantity f, in other words, that's the derivative of your antiderivative, then the definite integral of f prime, or the derivative of that, the antiderivative definite integral of that derivative from a to b gives the total change, or the net change, of f on that interval from a to b. So basically, if you look at this is saying the integral of a derivative gives you whatever the function is, but the difference of that function from the two endpoints. Okay, so here's example 9, bottom of page 326. Now, let's see how we're doing on time. We go to 11:40, so don't let me run over too badly. A chemical flows into a storage tank at the rate of 180 plus 3t. Anytime you see rate, think derivative. Okay, so I'm going to call that rate dc dt. Okay, so let me write that down right over here, if I can find it right here. This will be dc, that's the change of the chemical as a function of time. Rate usually means a time derivative. So that's what this represents. And sure enough, t is your independent variable here. Liters per minute. So maybe I should have... Okay, I'm sorry. It's not the rate of chemical flow. I was thinking it is. It's the rate of fluid flow. Okay, so this may be... let's leave C to represent capacity. How many liters per minute? So the T is in minutes now. Okay, where T is a time in minutes, and T is something between 0 and 60 minutes. So it's somewhere within an hour, 0 hours to 1 hour. Find the amount of chemical that flows into the tank during the first 20 minutes. Okay, well, what we're saying then is this is the time rate of change. So the amount of chemical, let's just call it C of t, is equal to the integral from 0 to 20 of your dc of t. So this would be c prime of t dt. And that was exactly what we said. Whatever you take a derivative of, then integrate, you wind up with what you started. evaluated between these two. So this would be this thing here, this derivative here, the antiderivative of this derivative is, C of t. So that would be, I think so, let me make sure of this, 180 plus 3t evaluated from 0 to 20. Okay, and this would be 180 plus 120, no, 60, I'm sorry, I don't know where my brain is this morning, minus 180, because when you put the 180 back in again, so this is just 60. Let me see if I did that right. No, I didn't. Sorry, I didn't take the derivative. Sorry, I didn't integrate. Well, let's start over. Oh, I can't do it on this slide. Let's see if I can. Let's start this thing over. Okay. All right, start this over. All right. I got too carried away with myself here. The amount of chemical C of t, that's what we're calling it, and this will be C of 20 by the way, is the integral from 0 to 20 of that there, which is 180 plus 3t dt, and this is antiderivative of 180 is 180t plus antiderivative of 3t is 3/2 t squared, right? That's what we evaluate from 0 to 20 because we're dealing in minutes here. So this will be 3,600 because that 0 is here, plus, oh man, 3/2 of 400. T squared, 20 squared is 400. Okay? Now, half of 400 is 200. Okay? So this would be 3,600 plus 600, 3 times 200, and that would be 4,200. And that would be liters. 4,200 liters. Yeah, that's what they got. Okay. Now, I was getting the nomenclature here. This is your dc dt. When you integrate that, you get C of t. Because this is a derivative, you integrate a derivative, you wind up what you started. We just didn't know what that was at the beginning. So you actually integrate this, and you get that. Evaluate it between 0 and 20. There it is. All right, let's see how they do it. That C of t, they did a little C of t, be the amount of chemical in the tank at any time t. Then the C prime of t represents the rate at which the chemical is floating into the tank at any time. And that's what they told us. Okay? During the first 20 minutes, the amount that flows into the tank is the integral from C prime dt. That gives you your C of t. And that's the integral from 0 to 20 of this. Antiderivative of 180 is 180t. Antiderivative of 3t is 3/2 t squared. Evaluated from 0 to 20. And that gives you 420. 42, oh my goodness, I can't even read. 4,200 liters. They should put their units in there. Well, let's see, maybe they will at next. Yeah, so the amount of chemical that flows into the tank during the first 20 minutes is 4,200 liters. Does that make sense? Any part of it you want to see broken down? They did it just about as rapidly as I did, so is all that making sense? Okay, let's see what happens Another way to illustrate the net change theorem is to examine the velocity of a particle. Now this is on the bottom of page 326. Examine the velocity of a particle moving along a straight line where s of t is the position at any time t. Its velocity is then s prime of t, or ds dt. That's the velocity. So the integral of a velocity gives you the displacement, because the derivative of displacement gives you the velocity. So that definite integral represents the net change in position or displacement of the particle, okay, in that time interval. A and B are times. When calculating the total distance traveled by the particle, you must consider the intervals where v of t is negative and the interval where v of t is positive. Because just picture, if you're going along here in the positive direction, and then you turn and go back here in a negative direction, then turn and go back again, your net change is that integral, what you just did. But the total distance would be how far you went this way, plus how far you went this way, plus how far you turned around and went back that way again. So you have to consider when your velocity is positive, when it's negative, and then when it's positive again. If you're talking about the distance traveled, not the displacement. Displacement is just that integral. Distance, you have to intervene and calculate any place where the velocity may have been negative, and you have to add that basically twice. Okay. So to calculate the total distance traveled, integrate the absolute value of the velocity. Okay, and we started the day almost with that kind of a thing. So let's see what we've got here. So the displacement of a particle from A to B is simply the integral v of t dt, where wherever you were at the, oh, I'm sorry, down here. I was wondering where in the world they get these from. That's the area under this curve minus the area under this curve plus the area under that curve. That's the total displacement. Because actually what you did, oh yuck, you went ahead, you came back, and then you turn back again. Total displacement was the difference between beginning and ending. That's it. Okay. However, the total distance traveled would be the distance you traveled from A to this point. Then you flip this over, absolute value, and calculate the distance you traveled here, only make it a positive area. So flip that over here, and then you add to that this part here. So you have piecewise function. Absolute value bar does that. So that way you have to add this area. In total, you subtract it. In the total distance travel, you add its absolute value here. So you add that area in. Positive area, not negative area. So here's example 10 on page 327. All right. The velocity in feet per second of a particle moving along a line is v of t is equal to t cubed minus 10t squared plus 29t minus 20, where t is the time in seconds. What is the displacement of the particle on the time interval 1 to 5? Well, that's pretty straightforward because displacement is simply the integral, okay, from 1 to 5 of your velocity, which is t cubed minus 10t squared, ooh, that's ugly, plus 29t plus minus 20 dt. All right. Well, what's the antiderivative of t cubed? Anybody? T to the 4th over 4 minus antiderivative of minus 10t squared. That would be minus 10 t cubed over 3 plus 29 t squared over 2 minus 20t. And that's evaluated from 1 to 5. Pull out the calculators, folks. Okay, I don't think I want to do that one in my head, but I got to watch those signs. Okay, good news is your interval there is positive, which is good. Okay, let me get my calculator set up here. Okay, so let's plug them in. Oops, I'm going to have to turn my calculator this way to get your exponents. Okay, so it's going to be 5 to the 4th. That's your x to y key on my calculator. You may have other key on yours. So I press that key, press a 4, and then divide that by 4. Okay, minus 10 times, I already know what 5 cubed is. That's 125, so I'm going to shorten this, do 125, but divide that by 3, plus 29 times 25 divided by 2 minus 20 times 5, which I could have just written 100 there, equal total displacement about 2.08, and that would be in feet. So that would be, oh wait, no, I forgot to subtract the 1. Okay, minus 1/4, so I'm going to put 0.25. Minus a minus is a plus 10/3 minus a 29/2 plus 20. So I got about 10.7, approximately 10.7. I'll say 10 2/3 because that's what it is exactly. I'm sure they didn't put it in the book. Well, they did 32/3, which is exactly what they did. Okay, so that came out 32/3. Yeah, that's what I got. But what's the total distance traveled by that particle? Okay, here we have to figure out where v goes negative, where your velocity goes negative. So what we have to do there is find out your zeros of your velocity function. Now let's just start from the beginning and see what is it when t is equal to 1. That's fairly easy to do. When t is equal to 1, the velocity is 1 minus 10, that would be minus 9, plus 29, that would be plus 20, minus 20 is 0. So it's starting out at 0 when t is equal to 1. Now, the question is it increase or does it decrease? So let's do t equal 2, just to see what it's doing there. When t is equal to 2, this will be 8 minus 40, so that would be minus 32, plus 58, so that would be goodness, I can't even remember what I just said. Let me write it down. Okay, when v of 2 is equal to 8 minus 20, wasn't it? No, 40. 8 minus 40. I can't even think. Plus 58 minus 20. Okay, 8 and 58 would be 66 minus 60. So it's positive. So it looks like it starts at 0 and goes positive for a little while. Okay, so what we have to do is find our zeros. Okay, so we're going to set this one equal to 0. Now, I don't know if you remember back from pre-calculus algebra, we got 6 minutes and this may take a while. From pre-calculus algebra, how you find the zeros, okay, of a polynomial function with real coefficients, with integral coefficients, I think it is, there it is, okay, they're always going to be of the ratio of P over Q, where P are all the possible factors, or it's Q over R. I don't remember how they did. Q over, yeah. Anyway, all the possible factors of this over the possible factors of that. So what are those? That was just plus or minus 1, plus or minus 2, plus or minus 3. We're not going to deal with the minuses, so let's just leave off those. 3 will not go into 20. 4 will go into 20. 5 will go into 20. 6 won't go into 20. 7 won't. 8 won't. 9 won't. 10 will go into 20. And then 20 will go into 20. Okay? Those are all your possible zeros. Okay? Now, we're only interested in the ones from 1 to 5. We already know that 1 is a 0. Okay? So 1 is a 0. So let's see if any of the rest of those are. We just did 2 and found out it's not a 0. Let's do 4. Okay? Let's do synthetic division. I think I'll come down here and do synthetic division. Okay? 4 into 1 minus 10, 29, and minus 20. Okay? Skip a line, draw a line, bring down the 1. This will be 4 minus 6 minus 24, 5, 20, 0. Ding, ding, ding. 4 is a 0. All right? I'm really suspicious. What happens if we do 2? Did I calculate that right? 2 into 1, negative 10, 29, and 20. Skip a line, draw a line. 1, 2, negative 8. Yuck! I get too near the bottom of the page and everything screws up. That's a negative 8 down there. So I'm going to put the 8 on top. And then that would be minus 16. This will be 13. And this will be 26. Yeah, we did it right. So yeah, that was 6 there. I don't remember what we got, but it's not 0. So 1's a 0, 4's a 0. Let's see if 5's a 0. Okay, doesn't really matter, but let's see. 5 into 1 minus 10, 29, and minus 20. Skip a line, draw a line. 1, 5, minus 5, minus 25, 4. Yes, that is a 0 also. Okay, so 1, 4, and 5 are zeros. We know that at 2 it's positive, and because that's a single 0 there, it's negative between 4 and 5. So I don't think we're going to have time to do it, but here's what our function would be. The total distance would then be, I'm just going to call that d, is equal to the integral from 1 to 4, that's where it's positive, of this thing, t cubed minus 10t squared plus 29t minus 20 dt plus, Okay, now what we're going to do here is do the opposite of that. So that would be the integral from 4 to 5 of minus t cubed plus 10t squared minus 29t plus 20 dt. All right. Now, we've already done what this one is. If I can get it. Here's what it is. Where is my pen? There it is. Okay. Here's what the antiderivative of the first one is. Okay. But this time we're only going from 1 to 4. So we're going to change our calculation here. I'm going to do that on my calculator. I don't know if I will or not. No, I've got 1 minute. Okay. Don't think I'll do it. Let's get it our best shot. Okay. Okay. Trying to get my calculator. Oh, there it did. Okay. So that's 4 cubed. 4 to the 4th power. I could have done that in my head. Divided by 4 minus 10 times 4 cubed is 64 divided by 3 plus 4 squared is 16, half of 16 is 8, 29 times 8 minus 80. All right, I got 2.66 of something another. Okay, let me write that down. That's 2 2/3. Okay, now I'm going to do the other one. Okay, and this will be a minus t4 over 4 plus 10t cubed over 3 minus 29t squared over 2 plus 20t. We'll evaluate. Oh, I forgot to subtract my 1. Yeah, we're out of time. Okay, that was just the first part here at 4. We have to subtract it at 1. So you got to go back and do that. You want to finish this over the weekend, or do you want to do this in class when we come back? I'll ask you. What you think? Anybody? Have I put you all to sleep? Okay, we'll pick it up. So what we're down to is we'll start with this step right here, bottom of page 327. So let's see, homework exercise. Oh, we came that close to finishing. Okay. 5.4, do either 5 or 7, they're both a calc chat. Any of the odds 9 through 33, they're all at calc chat, 17's at calc view. Do either 35 or 37, both at calc chat, 35's at calc view. Do any of the odds 39 to 43, they're all at calc chat, 41's at calc view. Any of the odds 45 to 49, they're all at calc chat, 45's at calc view. Any of the odds 51 to 55, they're all at calc chat, 55's at calc view. Any of the odds 57 through 57 or 59, they're both at calc chat. 61's both at calc chat and calc view. 63's at calc chat. 65's at calc chat. Any of the odds 67 through 73, they're all at calc chat, with 69 being at calc view. 75 to 79, all at calc chat. 75's at calc view. 81 to 85, all at calc chat. And then 87 through 91, they're all at calc chat. 93 through 97, they're all at Calc Chat with 93 at Calc View. You can explore doing 99 or 101 if you'd like. They're both should be at Calc Chat. 103 should be at Calc Chat. 105 and 107 are error analysis. I really don't care for those too much, but there is some instructional value to them. Be careful with them. Those should both be at Calc Chat. 109 should be at Calc Chat. Boy, they got a lot of them here. 111 or 113 should be at Calc Chat, and stop there. Okay, please stop there. And we will pick up, we'll start next time with just doing that last calculation there on page 327, and then we'll move on to 5.5. All right? Any questions? All right, I'm going to thank you so much. Appreciated that. Let me do it. Well, I was trying to do it with my finger, and I can't do that. I mean, on my